Hi, today in my project I'm going to talk about biomagnetics. Here's a quick rundown of the topics that will be included. Biomagnetic field sources, some simple mathematical principles to derive some of the stuff that I'm talking about, and then methods of measurement, how they're currently used in the field. So without further ado, biomagnetics was kind of a interesting topic for me because I figured we studied electrical currents and their role that they play within cells. We looked at the Hodgkin-Huxley model, and studying physics, I figured, well, if we are looking at electric fields, certainly we should also be taking a look at magnetic fields. In physics, we studied that any electrical current will generate a magnetic field and vice versa. So that's kind of where my idea came from. So with that in mind, bioelectric currents generated by propagating action potentials give rise to electrical potentials that are detected using electrodes. That is what Hodgkin and Huxley used on the squid. So some examples of that are ECG machines, EEG machines. They are used to study the heart and the brain respectively. So with that being said, those same bioelectric currents produce measurable electrical potentials that generate magnetic fields that can be detected using superconducting quantum interference devices, or SQUIDs, as they're called. So almost all biomagnetic measurements are made with SQUID systems, as they are without rival in terms of sensitivity. It is the existence of reliable SQUID magnetometers that has catalyzed the development of biomagnetism. But I will say that that is not the only way, and that's what I'm going to talk about later in this presentation, so stay tuned. So this is a quick illustration of how SQUIDs work. So we have bioelectric current sources that generate volume return currents, and these are the solid lines that we see here. So these are our electrical current lines that induce surface potentials that can be measured using contacting electrodes. So here are our electrodes, and again, they can be measured with ECG or EGG machines. The biomagnetic fields are the dashed lines, and they're generated by both the source and return currents and are detected outside of the body without having to use electrodes. So electrical signals are attenuated by inhomogeneous conductivity distribution within the body. So they are affected by these insulating components like the bones and air spaces that reduce potentials at the skin surfaces, which means that they're prone to be errors when detecting them. On the other hand, because of the low permeability of living tissue, the magnetic signals, however, generated by these bioelectric currents are not significantly affected. So these are more easily measured, so to say. Now, that's not to say they're perfect. There are some problems with them, as we will talk about a little later on, but because they do have a somewhat measurable magnetic field, that's what we're going to talk about now. So herein lies a problem with these biomagnetic signals. These fields are extraordinarily weak. A given biomagnetic source can be orders of magnitude lower than the typical background fields encountered in your typical laboratory or clinical environment. So these noise factors and difficulties associated with handling the way that the SQUIDs actually operate. So to kind of give us a background, before I go too much into how the SQUIDs actually operate, the magnetic vector fields enable greater source localization compared to scalar electrical potentials. So this is why it's easier to measure these magnetic fields as opposed to the electrical ones. It's actually a mathematical reason. Biomagnetic measurements of action potential, bioelectrical currents, and intrinsic magnetization are non-invasive and require no electrical contact with the subject and can provide both real-time and spatial information. So again, because we're measuring vector fields as opposed to these scalar electrical fields. Superconductivity is the underlying principle with which the SQUID relies on to operate, and it's characterized by resistanceless flow of electrical currents below a critical transitionless temperature that depends on the actual material itself. And what I mean by that is that there is a low temperature fluid, in this case it would be helium, that is used to operate the SQUID, that's used to cool it down after operating. Now, the SQUIDs themselves are based on three principles: the physics of superconducting state, quantization of magnetic flux and a superconducting loop, and quantum tunneling of superconducting Cooper pair electrons. Now, because of the knowledge and time constraint that is required to understand these principles. I'm not going to get too much into them, but I will say that a squid is constructed a superconducting loop interrupted by one or two insulated regions through which a supercurrent can flow by quantum tunneling. I definitely recommend looking into that and kind of delving into some of the mathematics because it is kind of neat how it works. But I will talk about some of the equations that do govern how we actually measure the biomagnetic signals. So apart from the quantum mechanics, the science behind this technology also stems from Maxwell's equations and the Biot-Savart law, which can be seen here. So the Biot-Savart law gives a magnetic field at some location R due to the bioelectric current density J at some location R prime, where we measure the volume integral evaluated over the source current. So for current sources, the volume integral can be approximated on the right-hand equation that you see, where Q is equal to the current dipole moment with a current I propagating in a direction D. So a current dipole can be thought of as a current source and sink separated by some displacement D pointing from the source to the sink, so where it originates and its path back. So in squid magnetic sensor arrays, it is necessary to calibrate after cooling because the holder of squid magnetic sensors must be non-magnetic and is usually made of plastic and inevitably becomes strained at cryogenic temperatures, which is what the squid is used to operate. So there's another technique that is kind of evolving right now. It's room temperature magnetic sensor arrays, and they have no strain at cryogenic temperatures because they're not exposed to them, hence the name room temperature. However, there is some non-negligible variation in the performance of these magnetic sensors because they're still they're still being developed and the science behind it is still evolving. And appropriate reproducibility of the manufacturing sensors has not been well established yet. So as the technology and science advance, the field of biomagnetics looks to expand. So us as engineers, we look to improve these systems. So currently, squids are expensive, bulky, and they require these liquid helium cooling devices called dewars to operate. And like I said, they require magnetic shielding, one or two insulation layers, because of the sensitivity of the magnetic fields. And here we can kind of compare the results of some squid versus RT sensor measurements. As you can see, so one is more finely tuned than the other. Here we have the RT sensors, and here we have the squid measurements. So again, it's an evolving science, and again, us as engineers, we may have something to look forward to in the future where we can apply our knowledge of biophysics. And with this, I conclude my presentation. Thank you.